see here. Wait for it to go live. I'll do a sound test, then I'll mute. You try talking, I try talking.
You want me to talk right now?
You try talking, I try talking.
You want me to talk right now?
All right. Yep, we're good. Cool. Mute it. Play. Yep, we're good.
All right, I'm muted.
Mute. We should be set.
All right.
Should be. Let's see if anybody hops on.
We just went down in number. We had people on, and then they went off.
That's funny. Well, I got the sound check in, so I don't need to check with my phone. Yeah, that's why we have one watching, because it's probably you watching it go live.
Okay.
Because I did not hit the play button.
Yeah, it's just me.
Oh, that's fine. I say when in doubt, let's go.
Yeah?
All right. Here we go, folks. Last time we met, we were talking about convection, a process by which the density differences between materials are going to bring about movement. So you have things that are less dense, and they tend to float upwards above the things that are more dense. So we had seen this in weather with the air. The warm air likes to rise up, and the cold air likes to sink, because warm air has lower density and cold air has higher density. And the same thing happens with that plastic mantle, the asthenosphere, that ooey gooey part of the mantle that can kind of flow. So where it is warmer, that asthenosphere, as you can see here, it says upwelling, is going to, the warmer is going to be less dense, and it's going to rise up, and it's actually going to split apart the plates, the rigid plates, the hard plates on top, and that's going to cause this mid-oceanic ridge that you see in the screen. And then, once it cools off at the top, it's going to come back down, and you will get these areas where the plates interact, they crash, and a lot of the time, one plate will go underneath the other. So that's what we're going to be looking at today. We're going to be looking at all the different things that happen when plates either meet or don't meet. They go away from each other. And different things are associated with each of the different ways that the plates move relative to each other. So, that's where we are. So there's three types of boundaries we need to talk about, and it's how they move relative to each other, like we said. So the first one is a convergent plate boundary. So with a convergent plate boundary, we have two plates that are headed for each other. Now, keep in mind, this isn't like bumper cars where they're going really fast and you get like a like, it's pretty slow. But there is a lot of energy. I mean, think about it. There's continents on the plates. They're even bigger than the continents themselves most of the time. And they're moving towards each other. And even if it's slow, there's just so much energy of them pushing into each other that this actually does create mountains where they like ripple into each other. So there's definitely a lot of energy, even though it's a slow process. But yes, in a continental, which we'll get into the difference, right? We talked about last time with density that there was the continental crust and the oceanic, the continental being less dense and the oceanic being more dense. If you have two continental plates that move together, they form mountains. And it's different if you have continental and oceanic, right? They're different densities. So we'll take a look at pictures to show how the two different types of plates and their interactions in a convergent, where they're headed into each other, we'll see how they look.
Right, they form different kind of features depending on the type of crust that it is.
So here we have an oceanic plate and a continental. and they are coming towards each other. Again, this is a convergent boundary. Convergent meaning that they are headed towards each other. And like we said, the oceanic is going to be more dense. So if you think about it like we had the tower with like oil and milk and the little bolt at the bottom, whatever has the higher density wants to go towards the bottom. Whatever has the lower density is going to go towards the top. So we've got the oceanic crust that is more dense, and it's going to sink when it interacts with this. They're not going to hit each other head on and move upwards or crumple. This one is just going to go underneath. We call this subduction, and it actually leads to, as you can see here, it leads to a trench being formed where the one plate going under kind of pulls the other plate down with it as it goes under. There's friction, right? This is rock that's moving against other rock. So it does grab it, pulls it down, and makes that deep trench. You also can get some water moving down. That water actually steams up that rock and helps to form some magma, which eventually could form some volcanoes along the coast. And yeah, that's what an oceanic and continental convergent boundary look like. Notice too that they've labeled lithosphere for the plates and asthenosphere for that ooey gooey part that moves underneath.
Right, that's what's helping to make the features that you see there.
Another cool thing is that as this oceanic crust is moving down, until this cuts off, until it remelts, because it's going down into a warm area where it's going to melt and form magma and go through the cycle. If it's still attached, it actually pulls the rest of the plate with it a bit too. So if you're wondering, like, well, how is it like pulling this other rock downwards? Wouldn't it just kind of get stuck and stop? Well, the reason is because it's like if you have a rope hanging off a table. If it drags a little bit off the table, it might pull a little bit, but as soon as you have a big chunk of the rope, it'll start to pull more and more and more of the rope that you had on the table. So with this piece of rock right here that's going downwards, if it's still attached and doesn't break off, it'll actually pull the rest of the plate with it, which I think is pretty cool.
Right, and that's what you see with the movement of the arrows.
So again, these are two plates that are coming together. We call that converging. One is oceanic, one is continental. So here's just another look at the same thing, right? Where you've got this subduction, one plate going underneath another, the trench being formed, and it shows you too that there are, from this, earthquakes. Right? Earthquakes are associated with plate boundaries, and so you can get some deep earthquakes or some shallow earthquakes. We're going to get into the difference between those and what an earthquake actually is and how it works on Monday. But just throwing it out there, earthquakes are certainly associated with certain types of boundaries. Okay. The next one is a continental convergent boundary. So this is where we have two continental plates that are going to come together. They are both the same density, usually, approximately. And so what's going to happen is instead of one totally sinking, like we had in the previous, one will sink a little bit, but because they are so close in density, more of the time they're going to, like if you take two pieces of paper and put them up against each other, they kind of move upwards, right? They kind of make a mountain range. It's the same idea, but here they're going to crumple upwards and you're going to get mountain ranges forming. So you can see that in the picture, and you can see kind of how that works in the animation at the top left. So here we don't have a trench, we don't really have much volcanism, but we do have mountain ranges being formed. And this currently is going on in northern India with the Himalayas. That is a part where there is a convergent plate boundary between two continental plates, and so that is rising.
Keep in mind too that it's a very slow process. It looks like it happens quickly in the picture, but it definitely does not.
This brings us to our last combination. So again, these are all convergent boundaries, where two plates are coming together. So we had oceanic and continental. We had continental and continental. The last thing we need to look at is oceanic-oceanic. So what happens? Well, it's extremely similar to oceanic-continental, where you have one plate that will be colder and therefore more dense, because it's just been in the ocean for longer than the other oceanic plate, and so you get another subduction zone. So right here you can see it'll form another trench, and the only difference is instead of those volcanoes being on land, you get a volcanic island arc. And there won't be volcanoes in a perfect line. They'll be a little bit more scattered, but as we'll see in a little bit, if you look at the ESRT, you can actually see where these island arcs are. So it's pretty cool. And again, this would definitely have some earthquakes associated with it. All right. So this is in your ESRT. Ooh, what page? 5?
I think it's 5.
I think it's
It's not 6. I think it's 5.
4 is the currents. Yeah, I'm pretty sure it's 5. Well, you can find it. You've got the ESRT. Well said. I don't have it memorized right now, though. Anyway, if you find this image, which we're both pretty sure is page 5, you can see on the bottom that there is the convergent boundary symbol, which is the bold black line with the rectangles along its side, and we put it in the box to show you where we can find one. You'll also see, if we go to that box and kind of blow it up so you can see it a little better, you can see that along it, it says the Peru-Chile Trench. We said, where you have these different plates coming together, you'll get subduction, right? And you can see over here where it says Nazca plate, that's the name of the whole plate, but this is like the ocean, right? It's oceanic plate. The ocean exists there coming into this continental crust. So it's going to subduct underneath it. Cool thing is that this also shows you which one is the plate that stays on top and which one is the one that subducts. You can see in the picture to the right, it says overriding plate and subducting plate. So the side that has those rectangles is the side that is going to be the plate that stays up, and the subducting is the one that goes down. So you can see there again that the Nazca plate, or the one that's to the left in the image, that one is the oceanic. It's going to subduct under. It doesn't have the rectangles on that side. So you can use the little symbols and the key that's on this image to help you figure out exactly which one is going underneath and which one is staying up. So again, the overriding plate is the one that stays on top, that does not go underneath, and that one has the rectangles on that side.
Right, that's always your key and how to remember that.
Gonna sneeze? Nope. Oh, nope. Good. Alright. So, that was just one type of plate boundary. That was a convergent plate boundary, and we had the 3 different, I guess you could call them subtypes, based on the type of crust that was there. The next type is divergent. So, again, the first one, convergent was together. The divergent was the opposite. So, plates move apart. You can see that in the animation on the top right. And this is where, like we had mentioned before, we get those mid-ocean ridges, those cool kind of underwater mountains with volcanism associated with them that are going to be making new seafloor. So volcanism caused by heat flow. We've got the Mid-Atlantic Ridge and the East Pacific Rise are both examples of mid-ocean ridges. And so the plates will be moving away from each other, making new seafloor, and pushing out to whatever plates are on their boundaries or borders. So this is shown by a little bit of a different symbol. Sorry. Instead of being a bold line, here you see it almost looks like a little tube that's like segmented. And you'll see the arrows too. If we blow this up, the arrows point away from each other, showing the movement. So this one does not actually have many different forms. There's no interaction of them hitting into each other, and this is usually going to happen in the ocean. And if it doesn't happen in the ocean and it happens on land, it quickly becomes the ocean because it's spreading the land apart, and eventually that fills in with an ocean over time. So this one, you don't need to remember a lot of forms. Just associate divergent plate boundaries with the ocean itself.
Typically where you have the divergent boundaries, you're going to have some sort of ridge. Depending on where it is, that'll give you the name of it.
Mm-hmm. Good point. They all have different names. And so the last type of plate boundary is going to be the transform. So instead of going away from each other or towards each other, this is going to be sliding past each other.
It goes like this.
So this is going to cause something called faulting, which we'll get into next time when we talk a little bit about earthquakes. And yeah, this is where you're going to find a lot of those earthquakes. So you all definitely know of a type of transform fault, the San Andreas fault. So here you can see the arrows again moving not at or away from each other, but opposite, right? Causing a lot of friction. And again, we'll get into how earthquakes work exactly, but for these, pieces of rock are stuck as they slide past each other. Eventually that little piece breaks. Well, I say little, relatively little. Like it'll have like an edge that gets caught, and then eventually it breaks, and you get a whole jolt as it tries to find and squeeze to a new position. So that's why you get so many earthquakes in that area. But the transform plate boundary also leads to some pretty cool pictures, which I suppose we'll show next time as well. So here is the summary of all those different plate boundaries, just taking it all in, because remember, it's all over the place. You've got different things that are moving away, and since they're moving away from here, well, whatever was moving this way, this might be interacting with something where it's got a convergent boundary. So you can look all over this and see, like, see here in the middle, you've got a ridge, and then this oceanic plate is interacting with this continental one. This is rifting, where we've got a continent splitting in two, causing a new ocean to form. So there's a lot going on, but key is we got to look at the boundaries and see what's going on there.
It's not anything you ever have to memorize. It's in the reference table. You look at the key and you can figure out the kind of boundary that it is.
Yep. And again, this entire thing is powered by convection, those loops, the density. So this asthenosphere right here is coming up, pushing out, and then coming back down and looping, something like this. So that is what is making the lithosphere, that harder, more rigid plate on top, move the way it does. So this is all really just powered by density. And that's pretty much it for today. Just looking at the boundaries. So
We'll
folks,
be posting an assignment in a little while. Office hours, same time as usual, right? 12:45 for you, Mr. Duprez, right?
yes, that is correct. 12:45 to 1:30.
And then 1:30 to 2:15 for me.
Yep. And of course, if you have any other questions you can't make office hours, make sure to email us.
Yep, we'll always answer you back.
And that's pretty much it. So I guess we'll wrap it up. Have a good day. Hope to hear from you soon, and get outside a little bit. It's starting to warm up.
Absolutely.
All right.
All right. See you guys next time.